Hi everyone, thanks for joining. Today we are pleased to have Dražen Glavan. He's going to talk about even photons, predicted OCT symmetry. So here you go, Dražen.
Good afternoon. Thank you very much. Thanks for the invitation. It's good to see Sabir again. Him and me were colleagues up until recently in Prague. So Sabir suggested that I would talk about vector fields in inflation, given that there might be some interest in it at your institute. So I'll try and do my best to arouse some interest. Well, perhaps for some of you that might know a little bit more about the topic, already the title should sound a bit silly or perhaps provocative, because you might know that vector fields, namely photons, are conformally coupled to gravity, and they don't really see the expansion of space-time themselves. So how in the world can they break any symmetries, or how can there be anything interesting going on with them? Well, so that came as a surprise to me as well. All of this is explained in these three papers that I cited just below the title. Very well. So if we can go to the next slide. So I thought first I tell you a little bit about, the kind of problems that I think about, the kind of problems that my research revolves around. So that might give you a little bit of a better perspective on, why I would look into this problem to start with. So my main focus of my research is on quantum field theory and inflation. And in particular, loop corrections and quantum corrections to dynamics of all sorts of fields in inflation. Now, why might that be interested other than, for the sheer curiosity of it? Well, I would say it's very interested due to this effect known as the gravitational particle production. That's originally due to Leonard Parker, who realized this back in the late 60s and early 70s, when I believe, as the story goes, not even his supervisor thought it would ever be of any relevance in any system whatsoever. And namely that effect of gravitational particle production, well, while it can be, much more formally, but sticking with let's say a pictorial description of it, you can imagine the standard picture of a quantum vacuum superimposed on an rapidly expanding and accelerating spacetime. So by the standard picture of a quantum vacuum, I mean this thing that they tell you about it in introductory chapters of books of QFT, where you kind of picture the vacuum of a quantum field not as something static, but something filled with continual quantum fluctuations, namely pairs of virtual particles popping in and out of existence continuously. So, well, if you imagine that picture superimposed on a space-time or on space that is rapidly expanding, you can imagine that, as this virtual pair of particles pops into existence, the expansion of space, if it's rapid enough, it can stretch it to large distances before they have a chance to recombine and disappear into the vacuum again. Now, if this expansion is very fast, and namely if the expansion is cosmological and there's a cosmological horizon involved, then you can imagine that, sometimes this expansion can pull this virtual pair to the distances larger than the horizon itself, which would then correspond to ripping this pair of virtual particles into reality, so ripping it from vacuum into existence. And then, of course, this process is not something that is extremely efficient, because we don't really see it happening today, and we know that the universe today is expanding, and in fact is accelerating as well. This effect is in fact sensitive to how fast the universe expands and how fast does it what's the rate of the change of the expansion, namely the acceleration. So really, where this is important is primordial inflation, this very brief but very extreme period of expansion in the history of our universe, where the universe expanded almost exponentially fast. So that's why I wrote in the top this so-called Friedmann-Lemaitre-Robertson-Walker metric, which in conformal coordinates just has this so-called scale factor a square in front of it that tells you how the physical distances grow with respect to the so-called co-moving or coordinate distances that are labeled by these points x. And during inflation, this ratio a dot over a is almost constant. That ratio is called the Hubble rate, or in this case, the Hubble constant. And then whenever it is a constant, the universe expands exactly exponentially fast in physical time. So it turns out that this Hubble rate h is large enough, and that the acceleration is fast enough so that you can have an appreciable gravitational particle production during inflation. And namely, this is already a three-level effect in the sense that it's really quantum fluctuations that are being amplified due to this rapid expansion. And this is basically the point where this neat picture of virtual pairs popping into reality, pairs of particles popping into reality, crumbles, because what you're really creating is field quanta with wavelengths that are larger than the horizon. So you're really creating some quantum fluctuations and not really particles. That's supposed to be depicted in this left picture. And this, yes, of course. Yes, I'm listening.
Dražen, people speak about
Sorry, Sabir, you're breaking up.
for them for packet that was crucial that is changing with time, right?
Look, I'm sorry, I really didn't catch anything.
Yeah.
You
For
said.
gravitational particle creation, can you hear? No.
Yes.
Look, for gravitational particle creation, it is crucial that the Hubble is changing with time for the process which Parker described. No? Oh, no.
So not really. You don't have to have a Hubble changing in time. In fact, it's more efficient if it doesn't change in time, if it's a constant. Well, I think it would be even more efficient if it grows in time, which would be super.
Твое там, okay. So sorry about this. Because there are two processes. One is which is usually called gravitational particle creation, and another is amplification of quantum fluctuations, right? And you assume that these are the same, or what?
So I'm unaware of the difference in the terminology that you're
okay,
describing.
It's the same. So you need just Hubble rate, and this will give you particle creation even if it's constant, like during the second, right?
Yes, that is correct.
Okay, just a matter of terminology. Okay, yeah.
Okay. So there are a couple of terms used for the same thing, I suppose. But what I'm trying to describe here is the effect that is behind the scale invariant power spectrum in primordial cosmological perturbations.
Okay.
I think that should answer it unambiguously for you, at least. And I would also say that this term gravitational particle production or creation is not a good term. It's really amplification of very long wavelength or very infrared quanta. That would be the correct name, I think. But it's a historical name. So Very well. And then this picture on the right is supposed to convey another message, which is that these three-level amplified quantum fluctuations in an accelerating expanding universe coupled to other things as well. So, for example, if this pair that is being created is charged, then this charge would presumably interact with some vector fields, and then you establish very long wavelength electric and magnetic fields due to the effects of interaction. Very well. So if we can go to the next slide, please. And so all of this that I described so far should actually be completely invalid for the main topic of my talk, which is photons in inflation. Why should this be invalid? Well, because this effect of gravitational particle production does not apply to all fields generally. It actually applies only to fields which are non-conformally coupled to gravity and which are either very light or massless. And photons, while they are massless, by photons I mean the electromagnetic field. I will always be using this synonymously. So while photons are massless, they are certainly conformally coupled to gravity, and they in fact don't see this expansion, and they don't experience gravitational particle production. And to see that why this happens, it's just enough to look what to check what their action is. So the first equation on this slide is the covariant action with a vector field U1 vector field A coupled to the metric G mu nu. If you were to evaluate this metric on a Friedmann-Lemaitre-Robertson-Walker or the cosmological background in conformal time, what you get is the lowest equation on this slide, which is just the Maxwell action for a photon in flat space. So photons really don't see their dynamics really doesn't see the dynamics of the expanding space up to some conformal rescaling, which is essentially just rescaling and not dynamics. So the most fair question to ask here: why in the world would you ever consider photons in inflation? Well, that's because they couple to other stuff. And the next slide, please.
Dražen, can I ask a quick question?
Sure.
Just super naive. All the gravity loop corrections, they don't give correction like Ricci scalar times a mu. It doesn't exist, right?
Well, so loop corrections generally give induce all sorts of effects, not only the local ones that you're referring to. But my comments were pertaining to the tree level only. So gravitational particle production is linear quantum fluctuations living on a classical expanding background. At that level, photons do not see the expansion. Up to corrections like the conformal anomaly and blah blah, which are extremely tiny. However, and what's the point of this slide is that photons do interact with fields which are non-conformally coupled to gravity, such as scalars and gravitons. And even if there aren't any scalars they definitely couple to gravitons. Now, gravitons get enhanced by a lot in inflation, and they interact with photons, however you want to represent the interaction. So let's say via loops. And that way they communicate the effects of the expansion to photons. So because of other quantum fluctuations that are sensitive to the expansion, the photons become sensitive themselves via interactions that are mediated to them. So I think that should answer your question as well, Sabir. Does it?
Yeah, thanks.
Okay, very well. So if if we think of, photons as a good probe of cosmological observables, which in many cases they certainly are, it does make sense to ask what kind of effects are communicated to photons in the early universe due to large fluctuations of other quantum fields which are non-conformally coupled. Namely, what are the effects that are communicated from very light scalars, which may or may not be there, and what are the effects communicated from gravitons, which would be the quantum gravitational effects. Well, so answering this question is a little bit involved technically, and typically the way one goes about is simplifications and idealizations, arguing more or less or better or worse, how much of the leading effect does it capture. And the most often implemented simplification or idealization when studying primordial inflation and loop effects in primordial inflation is the assumption of a de Sitter space background. The Sitter space background would correspond to an exactly exponentially expanding space, characterized by the Hubble rate being exactly constant and by this slow roll parameter being exactly 0. And why is that a big this is actually a very big simplification, and why is that? Well, it's because of enhanced symmetries that the de Sitter space exhibits compared to the more realistic inflationary backgrounds. So from the perspective of symmetries, the de Sitter space holds perhaps as prominent place as Minkowski space does, since it is one of the 3 maximally symmetric spaces. And in fact, it exhibits 10 isometries in 4 spacetime dimensions. And then when it comes to quantum field theory and our experiences with quantum field theory in flat space, it seems that the more symmetries there are and the more you can respect, the more symmetries you can respect at the more intermediate steps of your computation, the simpler it gets, the more transparent the results get, and the easier the understanding. So from that perspective, assuming a de Sitter space idealization ought to be very good and ought to make things much simpler and much more transparent, which indeed in many cases it does. However, there are some instances where this sort of reasoning actually can get you into problems. There are instances in the de Sitter space where, assuming that all the quantities you are working with respect the de Sitter isometries, the same assumption you would make in flat space that all the quantities you're working with respect Poincare invariances, where you would be correct to do it. In the de Sitter space, this doesn't always have to be true. And in the rest of the talk, I'll describe one particular instance where this happens not to be true, an instance that is somewhat surprising because it is photons, and photons do couple conformally to gravity, and they don't see this expansion. So if we could go to the next slide, please. Very well. So in these 2 slides, in this one and the coming one, I just drew a couple of examples of what you might be interested in computing in the early universe. Is what I was describing earlier. Computing these diagrams correspond to computing quantum gravitational, essentially quantum gravitational corrections to the dynamics of photons in the de Sitter space, where this curly lines correspond to gravitons. So you see in each loop there's one graviton, and these wavy lines correspond to photons. And the last cross, the cross in the last diagram just stands for counter terms. So that might be one of the questions you can ask. What are the corrections to dynamical photons as they propagate through expanding and accelerating space of primordial inflation, or what is the correction to, let's say, the Coulomb potential of charges in such an early universe. And then if we can go to the next slide, a similar sort of question you can ask, for example, in scalar electrodynamics. You can ask what are the corrections of photons to the dynamics of propagating scalars or scalar potentials, and vice versa, and so on. So this is just to flash some of the examples of the things you might want to compute, but I didn't want to discuss actually any loop computations in this talk. What I wanted to discuss primarily is the main constituents of those computations, which are the propagators. So if we can go to the next slide. All those wavy lines in the loops that I showed, they correspond to photon propagators, or, well, more properly said, to photon two-point functions, which are computed at the linearized level, so in the free theory. So as with any diagrammatic expansion, they're the main building blocks of that computation. It's just that compared to flat space, in expanding spaces, you need to worry about a different kind of problem. Namely, instead of solving a boundary value problem, boundary value in time, like you would do for scattering experiments in flat space, in cosmology, you're really wondering about the initial value problems and tracking time dependence of things and time dependence of correlators, etc. So instead of just computing Feynman propagators, you really need to contend with working with all of the propagators that you can write down. So the Feynman one that includes time ordering, the Whiteman one, which doesn't include any time ordering, and then their complex conjugates known as Dyson and, I guess, anti-Whiteman. I don't know whether the last one was named after a particularly distinguished person or not. Anyway, in the rest of the talk, I'll be talking about Whiteman and Feynman two-point functions of the photon field in de Sitter. So if we can go to the next slide, please. Very well. So a couple of slides back, I made a case that whenever you can respect symmetries of your problem, and whenever you can respect them at intermediate steps, it will make your life simpler, as the computations ought to simplify and shorten. This certainly is the experience in flat space, where, for example, doing the QAD computations in so-called covariant gauges versus doing them in Coulomb gauge, there's, I guess, about an order of magnitude difference in the complexity between the two, and the covariant gauge ends up being much, much simpler to use. So let's try to implement a covariant gauge for photons in de Sitter. So how does one go about doing that? Well, so it's most typically summarized by a so-called gauge fixing term, which is a term that you add to the three-level action that breaks your U1 gauge invariance. And the most general covariant one you can write down for photons is this last term in the first equation on this slide, is -1/2 psi d mu a mu square, where this nabla is now a covariant derivative, and g mu nu is the de Sitter metric, as it was before. Adding this gauge fixing term, which breaks gauge invariance, does respect all de Sitter isometries, as it is covariant itself. And as a bonus, you can write an arbitrary so-called gauge fixing parameter, which is just a constant psi, which at the end of the day allows you for explicit checks of gauge dependence of your observables. Meaning, if your observable, what you computed, it's supposed to be an observable, it cannot show any gauge dependence. That's what I mean by a check.
Can I ask a question? Did you
Yes.
just break the wild symmetry with guarantees that the field A mu lives like in flat space, like the scale factor factorizes, vanishes from action?
You are correct. This action is no longer conformally invariant. So this field mu will be sensitive to the expansion of space. That's completely true. Nonetheless, it should at least naively respect all de Sitter symmetries. But completely right.
Thank you.
In fact, you can make this choice such that it respects conformal invariance, but in that case, it cannot be covariant and have only two derivatives in it. I think you can put in more derivatives in the gauge fixing term, although I wouldn't do that. That will lead to other problems. Or you can explicitly break covariance and maintain conformal invariance, which actually ends up being a very good idea in practice. But maybe we can get back to that question at the very end, since it's not really directly related to what I'll be showing before the end.
Okay.
Very good. So what does one need to do to work out those propagators? Well, one needs to write down the equation of motion, which is this equation at the bottom of the slide, and then solve it. So box here is the D'Alembert operator, and R rho mu is the how do you call it, Ricci tensor. And the term that's proportional to 1 over psi on the left-hand side is the one that comes from the gauge fixing term in the gauge fixed action, and all the rest is just the covariantized Maxwell's equation, maybe written in a slightly less orthodox manner. But the solutions to this equation definitely do exist, and they're not that complicated to obtain. So if we can go to the next slide, please. They've been worked out a long time ago, in fact, in '86, so roughly around the time when I was born, they were worked out. In fact, arbitrary number of space-time dimensions d, but for a particular choice of the gauge fixing parameter xi equals 1, and they were worked out in a seminal paper by Allen and Jacobson, which is the one that they really looked into this matter for the first time, and they worked out a number of cases and also different gauges and also massive vector fields. However, what I'm interested in here is this particular case of de Sitter and massless vector field with a covariant gauge fixing term. So how did they go about solving this? I'll just briefly run you through the procedure for an arbitrary psi. Not only psi equals 1, the procedure is analogous, but the cases of arbitrary psi were then subsequently worked out by other people that I'll credit in a couple of slides. So a very sensible assumption is to assume that your two-point function will respect the Sitter isometries, and that's going to simplify things tremendously. The way you go about implementing this for vectors is you build up you build all your tensor bases out of scalars, more precisely biscalars that respect the Sitter isometries. So you build it out of this quantity y that depends on your 2 points and x prime. So that's why it's a biscalar, and this quantity is a conformally rescaled Lorentz invariant distance. It's rescaled by this factor h square a prime, and it is completely de Sitter invariant. And I've written here this I epsilon next to the time difference. This I epsilon is the Feynman I epsilon prescription, and this one corresponds to the Feynman propagator, but this I epsilon is different for all the 4 cases of two-point functions. That bears that is not really important in the rest of the talk. Which prescription we're talking about should be either irrelevant or clear from the context. But nothing really hinges crucially on that. So I could easily be talking about either Whiteman or Feynman two-point function. And that's why I'll often omit these plus minus Schwinger-Keldysh polarities that denote each of them. Very well. So once you've committed to your solution respecting de Sitter isometries, then all you need to do is write a de Sitter invariant ansatz for the two-point function. And there's two terms you can write. It's given in this last equation on this slide. So the first one being a double mixed derivative of this biscalar y, and the second one being a product of two first derivatives of y. And the only thing you do is you write arbitrary scalar structure functions C1 and C2 that can depend only on this biscalar. And what you need to do is plug it into the equation of motion, solve for C1 and C2, and you're done. So if we can go to the next slide, please. And in fact, there are pretty straightforward solutions for an arbitrary psi. They're given in these two first equations. And both C1 and C2 actually contain what can be recognized as a scalar two-point function in de Sitter. It's this function, this calligraphic f nu, that's written at the bottom of this slide, and it's a rescaled hypergeometric function 2f1 with certain parameters dependent on the number of dimensions, and this parameter nu, which in this case is d minus 3/2 or 1/2 in 4 spacetime dimensions. And then this hypergeometric function as an argument has 1/y/4, and then this y is this de Sitter invariant biscalar that I showed on the previous slide. So your scalar structure functions are just built out of scalar propagators and their derivatives or parametric derivatives. And very well, we're basically done. You've introduced a covariant gauge fixing term. It respects de Sitter isometries. You found a de Sitter invariant solution. Well, there you go. So I've essentially wasted more than half an hour of your life by now. But if we go to the next slide. Sorry. So before that, let me credit the people that worked out all the cases for arbitrary psis after Allen and Jacobson.
Can I ask
Yes.
a question?
Of course.
So in the definition of Feynman propagator, you have a t-time ordering. So naively,
Yes.
this is kind of coordinate dependent quantity. So
okay.
what would be your answer to that? Is it coordinate independent, or how do you define it?
So I would call time ordering really coordinate dependent in essence, in general, since it is it involves ordering in time rather than any sort of ordering in space. So I would say it's an object innately related to an initial value problem. So I wouldn't be bothered by it. But if you can form an actual, well, if you can form a question, I'd be happy to answer it. But if you ask for a comment, my comment is this.
No. The question is, what coordinates do you use to define your Feynman propagators, and does it depend on the coordinates where you define time ordering as the ordering in time coordinate? So you can
Okay, I
choose
see.
different.
I see. So I define it in conformal time coordinates, in which the line element is just a conformally rescaled Minkowski line element. But if you wanted to define it in terms of physical time, which is in which the line element is then just minus dt squared plus a squared dx squared. That would just require a coordinate transformation of the I epsilon prescription that I showed you.
Yeah. But what is worse, I can define it in absolutely different time. For example, in global de Sitter coordinates, which cover not just the point correct patch, but the whole de Sitter space-time. That like the whole hyperboloid, it looks like the function of time and coordinates. So it's not just a function of time.
Fair enough. So I would say that it depends on how you. It depends on the initial slice that you make. Once you decide on the slice where you would and where you can impose your initial data, I'd say that's what fixes it. Now, after that, any sort of coordinates you use are going to be immaterial, but it does matter how you choose the slicing.
So your answer is that I will get a different propagator for each coordinate system.
So yeah, I would say that if a de Sitter invariant state exists, then you shouldn't get a different propagator depending on the coordinate systems.
Okay.
In the same sense that if a Minkowski space, if a Poincare invariant propagator exists, then it's the same in every coordinate you use.
Okay.
If it doesn't, for example, for a massless minimally coupled scalar, there isn't an infrared finite de Sitter state, then yes, it would depend. So I wouldn't say that it depends on which coordinates you use. It depends on where you define your initial state.
I understand. Your claim is that for the de Sitter spacetime, there is a preferred choice, basically, of time ordering because of this symmetry group, large symmetry group.
So I'm saying that depends on the nature of the field. So for a massive scalar field, that there is a de Sitter invariant state, and that is an invariant claim. So in any coordinates. But so it's not only related to symmetry, it's also related to the nature of the field. Whether that field admits a de Sitter invariant state or it doesn't admit a de Sitter invariant state.
Okay, thank you.
Because, well, at least my understanding is if it doesn't admit a de Sitter invariant state, then it doesn't admit a de Sitter invariant two-point function in any coordinates. That's the case for a massless minimally coupled scalar, for example.
Okay, thank you. Yes.
All right, you're welcome. And I think it's a good question because so I just showed you that a de Sitter invariant solution for a photon exists, and it's built out of de Sitter invariant quantities, albeit I did define them in the Poincare patch and in terms of conformal coordinates, but that should be immaterial. This should be a propagator in any sort of slicing of de Sitter. And that is, in fact, how Allen and Jacobson derived it in the first place. Very well. So going back to this slide, so this gives credit to several people that worked out all the subsequent generalizations of the Allen and Jacobson results, so namely to arbitrary gauge fixing parameter. So if we can go to the next slide, please. Very well. So what I wanted to show you now is what happens when you take this de Sitter invariant solution and try to compute an observable. Like the simplest one-loop observable would be, well, in technical terms, a graviton tadpole, but in more sensible terms, an expectation value of the energy momentum tensor of the photon field in the de Sitter space. So why I say it's a graviton tadpole? Well, because this expectation value would be a source for the Einstein's equations, where it would then source the one-point function for the, metric fluctuation or the graviton. And the energy momentum tensor T mu nu would just be this loop part with the amputated leg in this diagram that I drew. So the first thing we need to contend with is that there are two possible definitions of the energy momentum tensor. namely, you have the first one I wrote, so this blue quantity, just T mu nu without any further labels, which is a definition descending from the just the covariantized Maxwell's action. So it's a variation with respect to the metric of the gauge invariant Maxwell action. The second definition, at least technically the second one, is the one that you get by varying the gauge fixed action. So that will be the Maxwell's one plus the gauge fixing term, which gives this contribution that I denoted in red, this T mu nu GF standing for gauge fixing. And I would say if anything is to make sense, these two need to give the same answer. Excuse me. So let's actually check whether they do. If you go to the next slide, please. And if you take my word for it without actually showing you the nitty-gritty of the computation, you do the two computations and then you get two different results for the expectation value of the energy momentum tensor, depending on whether you write down the gauge fixing term or you don't. That makes absolutely no sense. Gauge fixing should just be gauge fixing and shouldn't influence actual observables.
Excuse me, what is
yes.
xi in the second formula? Xi in the second formula.
Very
There
good.
should be xi.
Very good question. No, there isn't an xi. I was just about to comment on that. In fact, there isn't an xi. You compute it and you get just a something that's a finite number that seems to be independent of the gauge fixing parameter and seems to be, okay. That's the, another level of the issue. But sorry, were you asking whether there should be a dependence, or were you claiming that there should be dependence?
Yeah, but you basically answered my question. Thank you. So you expected that psi will, so you didn't expect this, that psi will not enter, but the answer will be gauge invariant, but finite, but different. Yeah. So this. Yeah.
I'll tell you right away where this conundrum comes from. If we can go just one slide back, please. You see, you have this 1 over xi in the lowest line in the definition of the red contribution to the energy momentum tensor, because you have 1 over xi dependence in the action itself. It will actually be the effect of 1 over xi multiplying something incorrect, and xi's happen to be canceling. That gives you this finite contribution. So if we can go, then yeah, thank you very much. So I call this a problem, and I call this a good motivation to actually take a look at what we've been discussing so far, namely to take a look at the propagator. So if we can go one slide further, please. Good. So why do I want to discuss the propagator? Well, let me give you one simple example to illustrate a point that not every solution to the propagator equation is a propagator or a two-point function of the, your quantum field. And by that, I mean like a proper expectation value of a product of operators. And a very simple example of this claim is a harmonic oscillator. So it satisfies the Feynman two-point function. So the time order product of x and x prime satisfies this simple ordinary second order differential equation in time. And you can write down a general solution of that equation. And it has a number of constants in it. Namely, this second to last equation contains both alpha, beta, and gamma as arbitrary constants of integration. Now, that might seem weird at first because it's a second order equation, and I wrote down 3 constants of integration, but this is really 2 equations. in one, because the differential equation with respect to time t and t prime have to be satisfied. So hence you have more constants of integration. However, if you appeal to, let's say, the uncertainty principle and to inequalities that you can easily derive, you get that all these parameters are not arbitrary. Namely, the product alpha times gamma must be larger than some quantity. And that's something you would never see by just writing the arbitrary solution. So even though this particular example technically doesn't have much to do with the photon propagator that I was discussing, it does illustrate the point that not every solution to the propagator equation is properly interpretable as your two-point function of your quantum field. So if we can go to the next slide, please. This same thing is true for the de Sitter invariant solution for the photon two-point function in de Sitter that I showed you before. And why is that? It is because this two-point function, not only does it have to satisfy the equation of motion, that's the second equation, I repeat the equation of motion there, it has to satisfy certain subsidiary conditions. Subsidiary conditions that come from the fact that your photon field is a gauge field. It's not an unconstrained field, but a system with first-class constraints. And in the quantum theory, the satisfying constraints can be mapped onto satisfying, can be mapped onto the requirement that the two-point functions of Hermitian constraint operators that correspond to the first-class constraint operators in a classical theory, those have to vanish. If those do not vanish, then in principle, your quantum theory allows you to measure fluctuations of constraints, which is nonsense. So these two-point functions of constraints can be translated into these three conditions that are written on the right, of the lowest three equations on this slide. So you have that you have it written in the form that a certain number of derivatives and contracted in a certain way when they act on the two-point function of the photon two-point function, they have to yield zero. These are the additional conditions that have to be satisfied for your two-point function to actually be the two-point function of your quantum field. And then if we go to the next slide, please. If you check these conditions for all the propagators reported in the literature, you actually find that most of them are satisfied except this first condition, which is not satisfied in almost every case, except in the so-called exact gauge case. That is due to my good collaborator, Richard Woodard, and his colleague, Nick Tsamis. All the other ones fail to satisfy this condition, meaning all the other ones, for all the other values of psi, are not two-point functions of your gauge vector quantum field. So how is that possible? Well, if we go to the next slide, please. And how is that possible, and how is that related to the problem with the energy momentum tensor that I mentioned? So if you actually take results from the literature and or that solution that I showed you a few slides back, and you compute what a double contracted covariant derivative acting on it, what it gives you, it doesn't give you zero, it gives you something that's proportional to this gauge fixing parameter psi, and then some dimensionful constant that's written in blue. By the way, d being the number of space-time dimensions. So immediately you can see that since this expression is proportional to psi, that it will vanish for psi equals zero, and that will be the reason why psi equals zero. The solution in psi equals zero is correct, the de Sitter invariant one. However, for all the other non-vanishing psi's, this will not vanish. And what this will cause when you compute the energy momentum tensor with this second definition, with this gauge fixing contribution included, because this doesn't vanish and it's proportional to psi, it's precisely the combination that appears when you do the computation, multiplied by 1 over psi, and this psi over psi gives you a psi independent contribution to the energy momentum tensor, which is precisely the difference, between 0 and non-zero value that I showed you a few slides back. So here you see a proof that the discrepancy in the results derives from the failure of the two-point function, the failure of the de Sitter invariant two-point function to satisfy all the conditions that it needs to satisfy. So even though you would get a result that seemingly seems fine and completely gauge independent, it would still not be correct. And it would actually come from a rather, whatever is the opposite of fortuitous, cancellation of the gauge of the dependence on the gauge fixing parameter. So the resolution of this should be to fix the propagator. So if we can go one slide further.
Okay, sorry, I had a question.
Yes.
So normally this constraints needs to be applied in the canonical quantization method, but if you calculate the propagators using the Feynman path integral, they should automatically be satisfied, aren't this the case?
Not really. In fact, whichever of the two formalisms you use, you should be doing one and the same thing. And I believe I'll show you I'll at least briefly show you both. So I won't show you the path integral formalism, but I'll show you BRST formalism, which I suppose you would use when you construct a path integral, right?
Okay, thanks.
Okay, good. So if we can go to the next slide. So a first comment on the canonical methods. Yes, very good. So the canonical methods in flat space are something that is very often called an outdated method of quantization. It goes under the name of this Gupta-Bloiler quantization. And it was, to me, it was mysterious for a great number of years, because it's always presented in this very ad hoc manner, where a positive frequency part of the d mu a mu operator of your photon field has to annihilate a state for that state to be a physical state. Well, I never really understood where that comes from. So, many years later, I managed to work it out, and in cosmology, and where this Gupta-Bloiler condition comes from is precisely from the condition that all your endpoint functions, well, in a free theory, two-point functions of your Hermitian constraints have to be have to vanish. Is this equation second equation from the bottom? Those are the conditions that I was showing you before for the photon two-point function. So these conditions happen to be equivalent to requiring that a non-Hermitian linear combination of your two constraints, the pi 0 and di pi I, that their non-Hermitian linear combination has to annihilate a state for it to be a physical state. And these two things happen to be equivalent. Now, the positive frequency part of d mu a mu that you see in Gupta-Bloiler quantization is precisely one particular instance of a non-Hermitian linear combination of pi 0 and di pi I. And it's one particular instance of it that manifestly respects Poincare invariance. However, you need not make that choice. In general, what you need is a non-Hermitian linear combination of your constraint of your Hermitian constraint operators to annihilate the state, and then automatically all the endpoint functions of constraints, what were first-class constraints in your classical theory, vanish. Now, I still don't know of a short or particular interesting way of describing this. So let me just translate this to a different language, which is I would say, less obvious to me, but much more followable and much more intuitive. So if we can go one slide to the next slide. Oh, in fact, so let's skip this slide. Let's go to the one after. Yeah, and that method is BRST quantization. So in BRST quantization, you introduce an additional structure. It ends up being equivalent to the canonical quantization. But in addition to this gauge fixing term, which has 1 over psi in it, you add another term to the action, this term C bar box C, which contains this Fadeev-Popov ghost and anti-ghost Rosmanian fields. And what you require now in this extended BRST fixed action is that there is a global symmetry, the so-called BRST symmetry, which kind of looks like a gauge transformation. It's this second equation from the bottom, but it's a global transformation because it's parameterized by this parameter theta, which is constant and not a field. You require that everything that is an observable, in this theory has to commute with a charge associated to this global symmetry, which happens to be this Q, this BRST charge. And moreover, you require every state of the theory to be annihilated by this Q. Now, this is the exact same condition as the Gupta-Bloiler condition. It's just that because it's extended by these fields C, you can write it in a way that is formally Hermitian. But in essence, this is one and the same, requiring one and the same thing. It's just that in BRST, you can write things so much more neatly. And then if we can go to the next slide, please. So if we can go straight to the bottom, if every state in a theory is to be annihilated by Q, this BRST charge, then the expectation value of any operator, of a commutator, of any operator with Q will have to annihilate, the expectation value of any commutator, of any operator with Q will have to vanish itself. Now, this is a very complicated way of saying that there has to be a Ward-Takahashi identity that the two-point function satisfies. Now, this is the relation written and at the bottom of this slide, and it's a single covariant derivative contracted into the two-point function, and that has to be equal to minus psi, the derivative of a two-point function of Fadeev-Popov ghost. So that's the quantity defined in the second line here. And since ghosts have their own dynamics, the third line gives you the equation of motion for the Fadeev-Popov ghost two-point function. And that equation of motion happens to be the equation of motion for a minimally coupled massless scalar field. So the ghost field satisfies exactly the same equation as a minimally coupled massless scalar. Now, why is that important? Because the ghost two-point function appears in the Ward-Takahashi identity. And the ghost two-point function satisfies the same equation as the minimally coupled massless scalar. And there is no de Sitter invariant solution for a minimally coupled massless scalar for the two-point function. So the quantity that appears on the right-hand side of the Ward-Takahashi identity is something that cannot respect de Sitter invariance. even when a derivative hits it, it cannot remove the de Sitter non-invariance. And that implies that the left-hand side will not be de Sitter invariant, and the left-hand side is the photon propagator. Now, if we go to the next slide, I believe there are more details on this. See, this is what happens when you take the photon propagator from the literature and you compute what is the action of a single contracted covariant derivative on it. You get the first term on the right-hand side in black, which would satisfy the Ward-Takahashi identity. And then you get an extra piece in red, which actually comes from the fact that you don't satisfy this identity. It comes from the fact that your de Sitter invariant solution cannot satisfy this identity, except in the limit when psi equals 0, where this red term vanishes. So this is a proof of the fact that your de Sitter, that your two-point function for the vector field cannot be de Sitter invariant, except in one particular case when the gauge fixing parameter vanishes. Now, if you were to take a second derivative on the left-hand side here, if you were to contract this with with nabla prime nu, that would correspond to those correlators I was showing you before, the two-point functions of the Hermitian constraints. That's exactly the same thing. So Ward-Takahashi identity is a single identity which incorporates all three that I was showing you before. So if we go to the next slide, please. So this is just a summary of all the equations that a photon propagator must satisfy. So the equation of motion, the Ward-Takahashi identity, and the ghost propagator needs to satisfy its own equation of motion. And then, as I was explaining you, if you go now from the bottom to the top, the last equation doesn't have a de Sitter invariant solution. Then the middle identity cannot respect de Sitter invariance. And then the equation of motion for the photon propagator cannot admit a de Sitter invariant solution. But I just showed you that it does admit a de Sitter invariant solution. However, the difference between the two is a homogeneous part of this equation. And only after adding this homogeneous part can you satisfy all the equations consistently. So if we go to the next slide, please. Right, so maybe we can, I think I've eaten up all my time already. So maybe we can just skip this. This is this slide and the next, that's an explanation why there is no de Sitter invariant solution for, this is fine, for the massless minimally coupled scalar. But a de Sitter breaking solution, which is a proper two-point function, you see when you act with a derivative on it, this last equation in blue, it has a de Sitter invariant piece, this first part that depends only on y, the scalar graphic f with an argument y, and then it has a de Sitter breaking part, which depends explicitly on the scale factor only and the zeroth component. And if we go to the next slide, please. If you account that in the construction of your photon two-point function, then what happens is that your de Sitter invariant solution, that will be the first line in black in this middle equation, is missing a piece. It's missing this contribution in red, which is a homogeneous solution to the equation of motion, but it breaks de Sitter. Only after you add this piece, then all the conditions are satisfied, all the endpoint functions of Hermitian constraints vanish, and you get a consistent answer for the energy momentum tensor. However, this extra piece, while it clearly it preserves spatial translations and rotations, it also preserves dilations, but it breaks spatial conformal symmetry, which is a part of the de Sitter group. Good. So if we go to the next slide, please. Very well. So as I mentioned, the computation of the energy momentum tensor now gives consistent results. And in addition, one property that changes is that your de Sitter invariant propagator, while in the deep infrared limit, so for large separations, it didn't go to zero, signaling, something rather odd in the infrared. With this de Sitter breaking correction now, it just asymptotes to zero as well. So that's a kind of a resolution of an odd property for free that we weren't even trying to solve. And I believe that's the main point of my talk, because I think the next slide, please, is just the conclusions. Very good. And I'll just leave these conclusions and for you to read, and I'll conclude my presentation with that.
Thanks very much. Any questions? Please ask.
Can I ask a question? So there are gauges where ghosts kind of decouple and you don't need them. Is psi equals to 0 exactly this gauge when ghosts are decoupled?
Yes, and not only that, at the linear level. So this was just the linear theory. Ghosts typically decouple. So here it doesn't even really depend on the gauge. Even if I had chosen a different gauge, the ghost would still be decoupled. That's always true. So you never really see it in. You typically never really see it in computations of loops, because they don't interact. So if they decouple at the interacting level, you won't see them in loops. Nevertheless, the Ward-Takahashi identity always exists, even at the linear level. Just that typically in flat space, whenever you assume Poincare invariance, everything is going to come out correctly. So you never see anybody checking, or even in textbooks, this is rarely checked or explicitly demonstrated that such an identity exists. However, in de Sitter space, and this is surprising, I don't want to criticize people for missing it. It was very surprising for me that this is not guaranteed.
Can I ask another question? Some absolutely stupid questions. Suppose you take a theory with ghosts, you calculate your incorrect propagator for the field a mu, but you add a tensor and calculate mean energy momentum tensor. But you add the mean energy momentum tensor of ghosts, just formally calculated, which is not allowed usually. Okay, but you add it anyway. Will you restore the correct answer in this strange way?
Good question. So I have a couple of slides after this one precisely on that question. So if you would go to the next one, please. So what you're asking me, I believe, is what you're asking me about is the second line in this first equation. So I add also the contribution from the ghost action to the energy momentum tensor, correct?
Yes.
Yeah, very good. So if I go then and compute things, I can express them in terms of 2-point functions in these 4 lines at the bottom of the page. Now, what ends up happening is that the red terms will cancel between themselves and the blue terms will cancel between themselves just by applying the Ward-Takahashi identity. So, and that's the naive identity that you assume is true even if your propagator is not true. But if we go to the next slide, so what will happen is that you will still remain with this first term, which doesn't cancel between ghosts and vector fields. It has to vanish by itself, but it can vanish by itself only if the Ward-Takahashi identity is satisfied.
Okay, thank you.
So the same problem appears if you don't use the correct propagator, regardless of how you compute the energy momentum tensor.
Okay.
Any other questions? Not really. Thank Dražen again. Thank you very much, and
Yeah, my
Yeah.
pleasure. Thank you for having me.
Yeah, no worries. Okay. Goodbye.
All the best in the new year.